we're going to drift into one of humanity's most profound questions. One that has captivated our imagination since we first looked up at the night sky and wondered what lies beyond. Can we ever find and travel to another solar system? Can we reach across the cosmic ocean and touch another world orbiting a distant star? In this gentle exploration, we'll journey through the remarkable discoveries being made right now, the incredible challenges that stand in our way, and the revolutionary technologies that might one day carry us to the stars. But before we begin, feel free to comment your time and location below. It's always amazing to see when and where we're all watching from as we contemplate our place in this vast cosmic neighborhood. Also, the visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination soar across the light years. I would love and encourage you to watch the video until the end, to learn many fascinating things about our cosmic future, but there is absolutely no problem if you doze off midway through. Let your thoughts drift among the stars. A gentle request that if you find comfort in these explorations of our cosmic destiny, I'd be grateful if you'd consider subscribing and liking this video. It helps the algorithm find more curious minds like us who wonder about humanity's place among the stars. Let's begin. As you settle into this moment of quiet wonder, perhaps with the gentle weight of evening settling around you, consider that above your head right now, invisible to your eyes but real nonetheless, are thousands upon thousands of other worlds. Each one a story waiting to be told. Each one a destination that might one day welcome visitors from Earth. The story we're about to explore isn't just about the mechanics of space travel. It's about the profound human drive to explore, to discover, to push beyond the boundaries of the known world and see what lies on the other side of the cosmic horizon. This is the story of exoplanets and interstellar dreams, told with the wonder it deserves and the curiosity that drives us to ask impossible questions about our future among the stars. The search for other worlds has transformed from science fiction to scientific reality in just the past few decades. We now live in an age of discovery that would have seemed magical to earlier generations. Every few weeks, astronomers announce the finding of new planets orbiting distant stars, worlds that exist in the habitable zones where liquid water might flow, where life as we know it could potentially take hold. In May of this year, scientists announced the discovery of Gliese 12b, an Earth-sized world that has captured the attention of researchers worldwide. This remarkable planet, located approximately 40 light-years from our solar system, orbits its host star every 12.5 days. What makes Gliese 12b so intriguing isn't just its size, comparable to Venus and only slightly smaller than Earth, but its estimated surface temperature of 42 degrees Celsius. This places it in that precious sweet spot where water could exist as a liquid, neither boiling away nor frozen solid. The significance of this discovery extends far beyond academic curiosity. Gliese 12b represents what scientists call the nearest transiting temperate Earth-sized world located to date. When we say transiting, we mean that from our perspective on Earth, this planet passes in front of its star as it orbits, creating tiny dips in the star's brightness that our sensitive instruments can detect. This geometric alignment is like winning the cosmic lottery because it allows us to study the planet's atmosphere using advanced telescopes, potentially revealing whether it might harbor conditions suitable for life. But Gliese 12b is far from alone in this cosmic catalogue of discovered worlds. Recent observations have also revealed Speculoos 3b, another Earth-sized planet orbiting an ultra-cool red dwarf star, just 55 light-years from our solar system. This world completes one orbit around its dim star in just 17 hours, making its year shorter than a single day on Earth. The star it orbits belongs to a class of cosmic objects that are among the dimmest and longest lived in the universe. Stars that could potentially provide stable conditions for billions of years longer than our own sun. The pace of these discoveries has been accelerating dramatically, thanks to sophisticated space-based telescopes and ground-based observatories working in unprecedented coordination. The Transiting Exoplanet Survey Satellite, known as TESS, has been adding to our stockpile of potentially habitable worlds since its launch in 2018. Each new discovery exceeds early expectations, revealing a universe that appears to be rich with worlds that could, at least in principle, support the kind of chemistry that gives rise to life as we understand it. What makes these discoveries even more remarkable is that citizen scientists are contributing to major finds through projects that analyze telescope data. Teams of astronomers and dedicated volunteers working together have discovered planets in the habitable zones of unusual star systems, including binary systems where two stars dance around each other while planets orbit in the gravitational balance between them. One such recently discovered planet takes 272 days to complete its orbit. A reminder that planetary systems can be far more diverse and complex than our own familiar arrangement of worlds. But of all the exoplanets discovered so far, one holds special significance for anyone dreaming of interstellar travel. Proxima Centauri B, located in the Alpha Centauri system, is the closest confirmed exoplanet to Earth at a distance of just 4.2 light-years. This proximity, while still representing an almost unimaginable gulf of space, makes it the primary target for any proposed interstellar mission we might attempt with foreseeable technology. Proxima Centauri B orbits its red dwarf star every 11 Earth days at a distance 20 times closer to its star than Earth is to the Sun. This might seem like it would make the planet unbearably hot, but red dwarf stars are much cooler and dimmer than our Sun, so the planet receives about 65% of the solar energy that Earth does. Its estimated equilibrium temperature places it within the range where water could exist as a liquid on its surface, situating it firmly within what astronomers call the habitable zone. Yet Proxima Centauri B presents both tantalizing possibilities and significant challenges. Any planet orbiting so close to its star would likely be tidally locked, meaning the same side always faces the star, just as the same side of our moon always faces Earth. This would create a world of permanent day on one hemisphere and eternal night on the other, with potentially extreme temperature differences between the two sides. The planet would also lack a strong magnetic field, leaving it vulnerable to powerful stellar flares and coronal mass ejections from its temperamental red dwarf host. However, recent climate modeling studies suggest that Proxima Centauri B might be more hospitable than these challenges initially suggested. Sophisticated simulations that include dynamic, circulating oceans show that even a tidally locked world could maintain habitable conditions. The movement of atmosphere and ocean currents could transfer heat from the day side to the night side so effectively that liquid water could be sustained in a band around the planet's equator, Even though the night side never sees starlight, the circulation of heat could create regions where life might flourish. The discovery of the complete Proxima Centauri system has revealed additional complexity that adds layers to our understanding of this nearby stellar neighborhood. Astronomers have identified at least 2 other planets in the system. Proxima D, one of the lightest exoplanets ever discovered, orbits incredibly close to the star at a distance of just 4 million kilometers, less than 1/10 of Mercury's distance from our Sun. This small world, with only 1/4 of Earth's mass, completes one orbit in just 5 days, racing around its star in the space between the stellar surface and the habitable zone. There's also evidence for a 3rd planet, Proxima Centauri C, though its existence remains disputed. If confirmed, this super-Earth would be at least 5 and 8 times more massive than our world and would orbit far outside the habitable zone, taking over 5 years to complete one circuit around the star. Intriguingly, this distant planet appears to shine much brighter than expected for its size, suggesting it might be surrounded by dust clouds or encircled by a ring system that reflects starlight. Understanding the complete architecture of the Proxima Centauri system is crucial for anyone planning an interstellar mission. The gravitational interactions between these worlds could affect spacecraft trajectories and influence the long-term stability of any probe we might send to explore this alien solar system. The presence of multiple planets also raises fascinating questions about the formation and evolution of planetary systems around red dwarf stars, the most common type of star in our galaxy. As we contemplate these distant worlds, it's important to recognize that finding potentially habitable exoplanets is only the first step in humanity's journey to the stars. The existence of these worlds, scattered across dozens or hundreds of light years of space, presents us with the most profound challenge our species has ever contemplated. How do we cross the vast cosmic ocean that separates us from these distant shores? The distances involved in interstellar travel are so enormous that they challenge our ability to comprehend them. When we say that Proxima Centauri B is 4.2 light-years away, we're describing a gap of about 25 trillion miles. To put this in perspective, if Earth were the size of a grain of sand, Proxima Centauri would be about 4 miles away. If you could somehow travel at the speed of a commercial airliner, the journey would take more than 5 million years. Even our fastest spacecraft, pushing the boundaries of current propulsion technology, would require tens of thousands of years to reach the nearest star system. The Voyager 1 probe, launched in 1977 and now traveling through interstellar space, is moving at about 38,000 miles per hour relative to the Sun. At this velocity, it would take more than 70,000 years to reach Proxima Centauri, assuming it were pointed in the right direction, which it isn't. This is the fundamental challenge that stands between humanity and the stars. The chemical rockets that have taken us to the Moon and sent robotic explorers throughout our solar system are woefully inadequate for interstellar distances. These rockets, impressive as they are, achieve velocities that are barely a whisper compared to what would be needed to make interstellar travel practical. Chemical propulsion systems are limited by the energy density of their fuel and the physics of rocket exhaust velocities. Even the most efficient chemical rockets can only accelerate their payloads to a tiny fraction of the speed needed for reasonable interstellar journey times. The most advanced propulsion technology currently in widespread use for long-range space missions is the ion drive, which uses electromagnetic fields to accelerate charged particles to very high velocities. Ion drives are remarkably fuel efficient and can operate for years, gradually building up impressive speeds. NASA's DART mission, which successfully deflected an asteroid in 2022, used ion propulsion to reach speeds of about 15,000 miles per hour. Yet even this advanced technology would require 18,000 years, or about 2,700 human generations, to reach Alpha Centauri. The energy requirements for interstellar travel scale exponentially with desired speed, creating what appears to be an insurmountable barrier with any conventional propulsion system. To reach even 10% of the speed of light, which would still require more than 40 years to reach Proxima Centauri, would demand energy resources that dwarf anything currently available to human civilization. This is where our exploration takes us to the cutting edge of physics and engineering, to technologies that exist today only in laboratories and theoretical papers, but which might one day carry our descendants across the cosmic gulf to other worlds. The challenge of interstellar travel has inspired some of the most ambitious and imaginative engineering projects ever conceived, pushing the boundaries of what might be possible with advanced physics and revolutionary new approaches to space propulsion. As you drift deeper into contemplation of these cosmic distances and the worlds that wait beyond them, consider that we stand at a unique moment in human history. We are the first generation to know with certainty that other worlds exist around other stars. We can see them, study them, and begin to understand their properties. Yet we remain bound to our single planet, separated from these distant worlds by gaps of space so vast they seem to mock our deepest ambitions. But perhaps that's exactly what makes this moment so profound. We are like explorers standing at the edge of an uncharted ocean, knowing that distant continents lie beyond the horizon, beginning to plan the voyages that might one day carry us across the cosmic sea to shores we can only imagine. The technologies that might one day bridge these cosmic distances read like pages from science fiction, yet they emerge from the most rigorous physics and engineering research being conducted today. At the forefront of these revolutionary propulsion concepts stands nuclear fusion, a process that powers the stars themselves and might one day power our journey to them. Nuclear fusion represents the most promising near-term solution for practical interstellar travel. Unlike the chemical rockets that have carried us to the moon and throughout our solar system, fusion propulsion harnesses the fundamental force that lights the cosmos. When lightweight atomic nuclei combine to form heavier elements, they release enormous amounts of energy, according to Einstein's famous equation. The energy density of fusion fuel is millions of times greater than any chemical propellant, offering the possibility of achieving the velocities needed to make interstellar journeys feasible within human lifetimes. The concept of fusion propulsion has captured the imagination of space agencies and private companies worldwide. In the United States, Congress has approved significant funding for the development of nuclear propulsion systems, specifically calling upon NASA to develop demonstration programs for both fission and fusion-powered rockets. The Russian Space Agency is collaborating with research institutes on plasma rocket engines that leverage advances in fusion plasma physics. These aren't distant dreams, but active engineering projects with substantial financial backing and clear development timelines. Recent breakthroughs in fusion technology have transformed what once seemed impossible into something that might be achievable within the next few decades. Depending on the specific design, fusion-powered rockets could achieve exhaust velocities of 150 to 350 kilometers per second. To appreciate what this means, consider that such a propulsion system could carry a spacecraft to Mars in 90 days or less, compared to the 8 months required with conventional chemical propulsion. The implications for interstellar travel are even more dramatic. The Princeton Plasma Physics Laboratory has developed one of the most advanced fusion propulsion concepts currently under serious development. Their direct fusion drive represents a compact fusion reactor specifically designed for space applications. Unlike the massive fusion reactors being built for terrestrial energy production, which aim to generate hundreds of megawatts of power, these space-based systems are designed to produce only a dozen megawatts or so. This more modest power output results in a reactor that is smaller, lighter, and more practical for launching into space, while still providing the energy density needed for ambitious robotic and human missions. The potential of fusion propulsion extends far beyond simply reducing travel times within our solar system. Theoretical studies suggest that fusion-powered spacecraft could achieve significant fractions of light speed, opening possibilities that seemed forever beyond reach. If the fuel mass represents 95% of a spacecraft's initial mass, a fusion drive could accelerate the remaining payload to velocities of several hundred kilometers per second as it exits our solar system. While a journey to the Centauri system would still require several millennia with current fusion designs, this represents a dramatic improvement over existing capabilities and could enable robotic exploration missions within reasonable institutional timescales. But fusion propulsion is not the only revolutionary concept capturing the attention of interstellar mission planners. Perhaps the most ambitious and well-funded attempt to achieve interstellar travel within our current generation is the breakthrough Starshot initiative, a project that approaches the challenge from an entirely different direction. Rather than carrying fuel for propulsion, this concept envisions using powerful Earth-based lasers to accelerate tiny spacecraft to unprecedented velocities. The Breakthrough Starshot program was announced with an initial funding commitment of $100 million, with estimates placing the total mission cost between $5 and $10 billion. The project's founders believe the first spacecraft could launch by the mid-2030s, representing an incredibly ambitious timeline for such a revolutionary undertaking. The fundamental concept relies on what physicists call radiation pressure, the gentle push that light itself can exert on reflective surfaces. The spacecraft envisioned for this mission would be unlike anything ever built. Each probe would be centered around what the project calls a star chip, a fully functional spacecraft no larger than a computer chip and weighing less than a single gram. These ultra-miniaturized vessels would carry cameras, sensors, power supplies, and communication equipment, all packed into a device smaller than a postage stamp. Advances in microelectronics and nanotechnology have made such extreme miniaturization theoretically possible, though the engineering challenges remain formidable. Attached to each star chip would be a light sail measuring several meters across, but only hundreds of atoms thick. These sails would need to be among the most advanced materials ever created, incorporating quantum dot coatings, graphene layers, and other exotic substances to achieve the necessary combination of reflectivity, strength, and lightness. The entire sail would have a mass density of less than 1 gram per square meter, making it lighter than soap bubbles yet strong enough to withstand the intense forces of laser-powered acceleration. The laser system required to propel these tiny spacecraft would be equally extraordinary. The total optical power needed is estimated at about 100 gigawatts, roughly 100 times the capacity of the largest battery storage systems in the world today. Achieving this would require approximately 100 million individual lasers working in perfect coordination, their beams combined and focused through a phased array system spanning several square kilometers. The technical complexity of such a system pushes the boundaries of what current engineering can accomplish. When a starship passes in front of this laser array, it would be accelerated to approximately 20% of the speed of light within just 10 minutes, experiencing forces 10,000 times greater than Earth's gravity. The acceleration phase would deliver about 1 trillion joules of energy to each sail, more energy than many small cities consume in an entire day. If successful, these tiny spacecraft could reach the Alpha Centauri system in just 20 to 30 years, with their findings transmitted back to Earth over an additional 4-year communication delay. Yet for all its ambition and funding, the breakthrough Starshot project has encountered significant technical hurdles that illustrate just how challenging interstellar travel remains. The project's founders initially identified around 30 major problems that would need to be solved before anyone could send an interstellar probe anywhere. Research groups around the world have been working to understand and reduce the technology risks in these critical areas, but progress has been slower than initially hoped. One of the most daunting challenges involves getting the laser beams through Earth's atmosphere without losing focus or power. Atmospheric turbulence causes light beams to twinkle and distort, just as it makes stars appear to shimmer in the night sky. Correcting for this distortion would require millions of adjustments every second, demanding computational power and precision beyond anything currently available. The atmospheric correction system alone represents what some researchers consider the largest technical hurdle for the entire program. The financial requirements are equally challenging. To make the project economically feasible, the cost of laser power would need to decrease from the current price of $100 per watt to around 1 cent to 5 cents per watt. This represents a cost reduction of several thousand%, requiring breakthrough advances in laser technology that may or may not prove achievable within reasonable timeframes. Despite these formidable challenges, research continues on individual technological components, and the project has achieved some notable successes. Small test spacecraft called sprites have been successfully deployed in space to validate basic communication and survival systems. The fundamental physics underlying the concept appears sound, and no absolute deal breakers have been identified by the teams of expert scientists and engineers leading the program. Beyond fusion propulsion and laser-powered light sails, there exists an even more exotic possibility for interstellar travel, though it remains far more speculative than either of the approaches we've discussed. Antimatter propulsion represents the theoretical upper limit of rocket technology, offering energy densities that dwarf even fusion by enormous margins. When matter and antimatter come into contact, they annihilate each other completely, converting 100% of their mass into pure energy according to Einstein's equation. The energy release from antimatter annihilation is so enormous that even tiny amounts could power spacecraft to significant fractions of light speed. Virtually all the mass of the fuel converts into energy, making antimatter the ultimate rocket propellant for any civilization advanced enough to produce and store it safely. The highest energy density fuel possible in our universe could theoretically propel multi-ton spacecraft to relativistic velocities, enabling interstellar journeys measured in decades rather than millennia. However, the technical challenges associated with antimatter propulsion make even fusion rockets seem simple by comparison. Current antimatter production capabilities are billions of times smaller than what would be required for interstellar missions. The few hundred antimatter particles that can be produced and stored in the world's most advanced facilities would need to be increased by 23 orders of magnitude to provide useful quantities of fuel. Storage times would need to increase from minutes to decades, requiring containment technologies that don't yet exist even in theoretical form. The production of sufficient antimatter would require energy resources that exceed the total power generation capacity of human civilization by enormous margins. It may be possible to dramatically increase storage capabilities by condensing antimatter into liquid or solid forms. But this too represents a technological challenge of staggering complexity. Many technical problems must be solved before antimatter propulsion could be considered viable, making it a very long-term prospect that might not be achievable for centuries. As we contemplate these various approaches to interstellar travel, we must also consider the hostile environment that any spacecraft would encounter during the journey itself. Interstellar space is not the empty void it might appear to be from our perspective within the solar system. The space between stars contains dust, gas, and high-energy particles that pose serious threats to spacecraft traveling at the velocities required for practical interstellar missions. When a spacecraft accelerates to relativistic velocities above 30% of light speed, the thin interstellar medium becomes a flow of high-energy particles bombarding the vessel like hard radiation. Every atom of hydrogen or helium encountered during the journey would impact the spacecraft with the energy of a cosmic ray particle. Electronic equipment, structural materials, and any biological passengers would face radiation doses far exceeding anything experienced by spacecraft within our solar system. The radiation environment in interstellar space is fundamentally different from what we encounter closer to home. Beyond the protective influence of our sun's magnetic field and solar wind, spacecraft must contend with galactic cosmic rays, high-energy particles accelerated by supernova explosions, and other violent cosmic events. These particles can penetrate deeply into spacecraft materials, causing cumulative damage over the years or decades of an interstellar journey. Shielding against such radiation presents enormous engineering challenges. Traditional radiation shielding relies on mass, using thick layers of dense materials to absorb or deflect harmful particles. But for interstellar missions where every gram matters for achieving the necessary velocities, massive shielding systems could make the entire enterprise impractical. Advanced concepts include magnetic field generators that could deflect charged particles, or plasma windows that might provide protection while minimizing mass penalties. The dust and debris scattered throughout interstellar space pose additional hazards for high-speed spacecraft. At relativistic velocities, even microscopic particles become potential projectiles capable of causing catastrophic damage. A grain of sand encountered at 20% of light speed would impact with the force of a large explosive, potentially destroying any spacecraft unlucky enough to encounter it. Mapping the distribution of interstellar matter and developing protection systems capable of dealing with high-speed impacts represents another layer of complexity for interstellar mission design. As you drift deeper into contemplation of these challenges and possibilities, consider that we are exploring the very limits of what might be achievable with advanced technology and human ingenuity. The obstacles standing between humanity and the stars are not merely technical hurdles to be overcome with better engineering. They represent fundamental physical constraints that define the boundaries of what's possible within our universe. Yet within those boundaries lie possibilities that would transform our species from inhabitants of a single world to citizens of the galaxy itself. The question of when we might achieve interstellar travel brings us face to face with timelines that stretch across generations and engineering challenges that push against the very limits of physics itself. Yet even as we grapple with these seemingly insurmountable obstacles, remarkable progress is being made in laboratories and research facilities around the world, bringing technologies that once existed only in theoretical papers closer to practical reality. Recent advances in materials science are making previously impossible engineering concepts achievable. The development of ultra-thin, ultra-light metamaterials suitable for light sails has progressed from laboratory curiosities to materials that can be manufactured and tested in space environments. Researchers are creating substances only hundreds of atoms thick yet strong enough to withstand the intense forces required for laser propulsion. These materials incorporate exotic substances like graphene layers and quantum dot coatings, achieving combinations of properties that seemed impossible just decades ago. The miniaturization of spacecraft components has followed a trajectory similar to the computer revolution, with entire functional systems now fitting into spaces smaller than coins. Advanced sensors, communication equipment, and power systems can be integrated into packages weighing less than a gram while maintaining the functionality needed for interstellar exploration missions. This extreme miniaturization doesn't just make certain mission concepts possible, it fundamentally changes how we think about space exploration itself. Instead of sending single large spacecraft on interstellar journeys, future missions might deploy swarms of tiny probes, each no larger than a butterfly, yet carrying sophisticated scientific instruments. The redundancy provided by launching hundreds or thousands of such craft simultaneously could ensure mission success, even if many individual probes fail during the decades-long journey between stars. This distributed approach to space exploration represents a paradigm shift that could make interstellar missions far more resilient and scientifically productive. The development of advanced propulsion systems continues to accelerate, driven by both government funding and private investment. Compact fusion reactors specifically designed for space applications are moving from theoretical concepts to prototype systems that can be tested and refined. These reactors don't need to achieve the massive power outputs required for terrestrial energy production. Instead, focusing on the specific requirements of spacecraft propulsion, where efficiency and longevity matter more than raw power generation. Several fusion propulsion concepts are now receiving serious engineering attention and substantial funding commitments. The timeline for developing these systems has been compressed significantly as fusion technology advances across multiple applications simultaneously. Breakthroughs in magnetic confinement, plasma physics and fusion fuel cycles are accelerating progress toward practical fusion rockets that could revolutionize space exploration within the next few decades. But even as these advanced propulsion technologies mature, we must confront a sobering reality about the scales of time and distance involved in interstellar exploration. The nearest potentially habitable worlds lie years away, even at significant fractions of light speed. This means that any interstellar mission we launch will be a commitment that extends across generations, requiring institutional stability and technological continuity that challenges human civilization in unprecedented ways. Consider what it means to launch a mission that will take decades to reach its destination and additional years to transmit its findings back to Earth. The scientists who design and launch such a mission will likely never see its results. The technologies used to build the spacecraft will be obsolete by the time it reaches its target. The political and economic systems that funded the mission may have transformed completely during the journey. Interstellar exploration demands a long-term perspective that extends far beyond normal human planning horizons. This temporal challenge is compounded by the rapid pace of technological advancement. Any interstellar mission launched today using the best available technology would likely be overtaken by faster spacecraft launched decades later using more advanced propulsion systems. This creates what some researchers call the interstellar paradox, where waiting for better technology might always seem more rational than launching with current capabilities, potentially delaying interstellar exploration indefinitely. Yet there are compelling arguments for beginning interstellar missions as soon as technically feasible, even with imperfect technologies. The knowledge gained from attempting such journeys would advance our understanding of interstellar travel enormously, providing crucial experience for more ambitious future missions. The engineering challenges of building spacecraft capable of operating autonomously for decades in the hostile environment of interstellar space would drive innovations beneficial for all aspects of space exploration. The selection of target destinations for early interstellar missions involves complex trade-offs between scientific interest, technical feasibility, and mission duration. Proxima Centauri B remains the most obvious candidate due to its relative proximity, but other recently discovered worlds offer intriguing alternatives that might justify longer journey times. The diversity of exoplanets discovered in recent years provides mission planners with an unprecedented menu of potential destinations, each offering unique scientific opportunities. Some mission concepts envision multiple spacecraft launched toward different target systems, creating a portfolio approach to interstellar exploration that maximizes the probability of significant discoveries. Rather than placing all resources into a single mission toward one destination, this distributed strategy would provide comparative data about different types of planetary systems and stellar environments. The scientific return from such a coordinated exploration program could transform our understanding of planetary formation, stellar evolution, and the potential for life throughout the galaxy. The communication challenges inherent in interstellar missions add another layer of complexity to mission planning. Maintaining contact with spacecraft across light years of distance requires communication systems more powerful and sensitive than anything currently deployed for space missions. The time delays involved mean that spacecraft must be capable of autonomous operation for extended periods, making decisions and responding to unexpected situations without guidance from Earth. Advanced artificial intelligence systems will be essential for interstellar spacecraft, providing the decision-making capabilities needed to operate independently across vast distances and timescales. These systems must be robust enough to function for decades without maintenance, adaptable enough to handle unforeseen circumstances, and sophisticated enough to conduct meaningful scientific investigations of alien worlds. The development of such autonomous systems represents one of the most crucial enabling technologies for interstellar exploration. The data transmission requirements for interstellar missions push the boundaries of communication technology. Sending high-resolution images, spectroscopic data, and other scientific measurements across interstellar distances requires enormous amounts of power and highly directional communication systems. The spacecraft must maintain precise pointing toward Earth for years, while traveling at high velocities through environments that could disrupt sensitive equipment. Recent advances in laser communication technology offer promising solutions to these challenges. Optical communication systems can achieve much higher data rates than traditional radio communications, while requiring less power for transmission across interstellar distances. However, these systems demand extreme precision in pointing and tracking, requiring spacecraft to maintain their orientation with accuracies measured in tiny fractions of a degree throughout journeys lasting decades. The psychological and social dimensions of interstellar exploration present challenges that are less technical, but no less important than the engineering obstacles. Humanity has never undertaken projects that span multiple generations, requiring sustained commitment and resource allocation across timescales that exceed normal institutional memory. The social structures needed to support interstellar missions must be designed to maintain continuity across political changes, economic fluctuations, and shifting cultural priorities. Public support for interstellar missions will need to be cultivated and maintained across generations, who will never see direct benefits from these enormous investments. The educational and inspirational value of interstellar exploration must be communicated effectively to sustain the long-term commitment required for success. This represents a challenge in science communication and public engagement that goes far beyond traditional advocacy for space exploration programs. International cooperation will be essential for interstellar missions, as no single nation possesses the resources and expertise needed for such ambitious undertakings. The development of governance structures for interstellar exploration, including protocols for data sharing, mission coordination, and conflict resolution, will require unprecedented levels of international collaboration. These frameworks must be robust enough to survive decades of changing political relationships while maintaining the scientific integrity of exploration programs. The discovery of life on other worlds, even in microbial form, would represent one of the most significant findings in human history. Interstellar missions carry the potential to answer fundamental questions about the prevalence of life in the universe and our place within the cosmic community. The protocols for detecting, studying, and announcing such discoveries will need to be developed carefully, considering the profound implications for human understanding of our cosmic context. As we contemplate these challenges and possibilities, we find ourselves at a unique juncture in human history. We possess enough knowledge about exoplanets to identify compelling destinations for interstellar exploration, and we can envision technologies that might make such journeys feasible. even if they remain beyond our current capabilities. The gap between what we can imagine and what we can achieve is narrowing, bringing the prospect of interstellar travel from the realm of science fiction into the domain of serious engineering planning. The next few decades will likely determine whether humanity takes its first steps toward becoming an interstellar species. The technologies under development today, from fusion propulsion to ultra-miniaturized spacecraft, could mature into the systems needed for practical interstellar missions. The discoveries being made about nearby exoplanets continue to refine our understanding of potential destinations and the scientific questions we might address through interstellar exploration. Yet even as we push against the boundaries of what's possible, we must remember that the journey toward the stars is not just about reaching other worlds. It's about expanding human consciousness beyond the confines of our single planet, embracing our role as explorers in a universe filled with wonders we can barely imagine. The technologies we develop for interstellar travel will transform life on Earth. The perspectives we gain will reshape our understanding of our place in the cosmos. And the knowledge we acquire will benefit countless generations yet to come. The stars that shine above you tonight are no longer distant points of light, but destinations waiting to be explored. Some harbor worlds that might shelter life. Others offer insights into planetary formation and stellar evolution that could transform our understanding of the universe itself. The cosmic ocean that separates us from these distant shores is vast beyond comprehension, but it is not impassable. With determination, ingenuity, and the patience to think across generations, humanity may yet learn to sail among the stars. As you drift deeper into contemplation of these cosmic possibilities, consider that you are living at the threshold of the interstellar age. The decisions made in the coming decades about funding, international cooperation, and technological development will determine whether future generations inherit a single-planet species or a civilization that has begun to spread across the galaxy. The dreams we nurture today about traveling to other worlds may become the realities that define humanity's cosmic future. The engineering solutions being developed for interstellar travel reveal themselves to be as elegant as they are ambitious, pushing the boundaries of human ingenuity into realms that would have seemed impossible just decades ago. As we explore these revolutionary concepts, we begin to see how the challenge of reaching other star systems is transforming our understanding of what technology can accomplish and what human civilization might become. One of the most intriguing developments in fusion propulsion involves the creation of magnetic plasma drives that combine multiple advanced physics concepts into integrated propulsion systems. These designs leverage the incredible energy density of fusion reactions, while using magnetic fields to channel and direct the resulting plasma in ways that maximize thrust efficiency. The magnetic containment systems being developed for these drives represent breakthroughs in plasma physics that extend far beyond space propulsion, offering insights that could revolutionize energy production here on Earth. The fuel for these fusion systems comes from some of the most abundant materials in the universe. Hydrogen isotopes extracted from ordinary seawater could provide the energy equivalent of hundreds of gallons of gasoline from just a single gallon of processed seawater. This extraordinary energy density means that relatively small amounts of fusion fuel could power spacecraft to velocities that would make interstellar travel practical within human lifetimes. rather than requiring the millennia that current propulsion systems would demand. Recent theoretical studies suggest that advanced fusion drives could accelerate spacecraft to 10 or 15% of light speed, reducing journey times to nearby star systems from tens of thousands of years to mere centuries. While centuries still seem like impossibly long time frames from our current perspective, they represent journey durations that human institutions could potentially sustain. A mission launched today with such capabilities could reach its destination within the historical time span that separates us from the founding of major universities or the construction of great cathedrals. The development of these fusion propulsion systems is progressing along multiple parallel tracks, with research teams around the world approaching the challenge from different angles. Some focus on magnetic confinement fusion, using powerful magnetic fields to contain the extremely hot plasma needed for fusion reactions. Others explore inertial confinement approaches, where fuel pellets are compressed and heated using intense laser pulses or ion beams. Each approach offers unique advantages and faces distinct technical challenges, but all share the common goal of harnessing stellar fire for spacecraft propulsion. The compact fusion reactors being designed for space applications must operate under conditions far more demanding than their terrestrial counterparts. They need to function reliably for decades without maintenance, withstand the radiation and temperature extremes of interstellar space, and provide steady thrust while consuming minimal fuel. These requirements are driving innovations in reactor design, materials science, and control systems that push technology forward across multiple fields simultaneously. Beyond fusion propulsion, the laser-powered light sail concept continues to evolve as researchers address the fundamental challenges that initially seemed insurmountable. The atmospheric distortion problem that plagued early designs is yielding to advances in adaptive optics and atmospheric correction systems. These technologies, originally developed for ground-based astronomical telescopes to compensate for atmospheric turbulence, are being scaled up and adapted for the far more demanding requirements of interstellar beam propulsion. The laser arrays needed for such missions are becoming more feasible as laser technology advances rapidly across commercial and scientific applications. The cost of laser power has been declining steadily, following technological learning curves similar to those seen in solar panels and computer processors. While the required cost reductions are still substantial, they no longer appear impossible given the trajectory of laser technology development. Recent breakthroughs in laser efficiency and power scaling have demonstrated that the massive laser arrays envisioned for light sail propulsion could be built using technologies that are approaching commercial viability. Solid-state laser systems with unprecedented power outputs and efficiency ratings are being developed for industrial applications, and these advances directly benefit the requirements for interstellar propulsion systems. The spacecraft themselves continue to benefit from the ongoing miniaturization of electronic components and scientific instruments. Modern sensors can detect and analyze atmospheric compositions, surface materials, and magnetic fields using devices smaller than postage stamps. Communication systems that once required room-sized equipment can now be integrated into packages weighing less than a paperclip, while maintaining the signal strength needed to transmit across interstellar distances. These advances in miniaturization enable mission concepts that would have been unthinkable with earlier technologies. Instead of launching single large spacecraft, carrying comprehensive scientific instruments, future interstellar missions might deploy clouds of specialized microprobes, each optimized for specific types of measurements or observations. This distributed approach provides redundancy that dramatically improves mission success probability, while allowing for more comprehensive exploration of target systems. The scientific instruments being developed for these miniaturized spacecraft represent marvels of engineering that compress laboratory quality analysis capabilities into packages measured in grams rather than kilograms. Spectrometers that can identify atmospheric gases, cameras capable of resolving planetary surface features, and magnetometers sensitive enough to map magnetic fields around distant worlds are all being designed to fit within the severe size and weight constraints of interstellar probe missions. Advanced materials science is enabling the construction of light sails with properties that seemed impossible when the concept was first proposed. These ultra-thin membranes must be lighter than soap bubbles, yet strong enough to withstand acceleration forces thousands of times greater than Earth's gravity. They must reflect laser light with near-perfect efficiency, while remaining stable across temperature ranges from near absolute zero to the intense heat generated during acceleration phases. The development of these materials draws upon advances in nanotechnology, quantum physics, and materials engineering. Graphene layers, just atoms thick, provide structural strength while maintaining minimal mass. Quantum dot coatings optimize light reflection across specific wavelengths. Metamaterials with properties not found in nature are being designed and manufactured to meet the unique requirements of interstellar light sails. Testing these advanced materials and systems presents unique challenges that are driving innovations in space-based research platforms. Small test spacecraft are being deployed to validate technologies in the harsh environment of space, where they face radiation, extreme temperatures, and the vacuum conditions that interstellar probes will encounter. These tests provide crucial data about how advanced materials behave under space conditions and help identify potential problems before they affect full-scale missions. The communication systems required for interstellar missions are advancing along with improvements in laser technology and precision pointing systems. Maintaining communication links across light years of distance requires power levels and antenna precision that exceed current space communication capabilities by enormous margins. Yet recent advances in optical communication and precision attitude control are making these requirements achievable. Deep space communication networks are being enhanced to support future interstellar missions, with new antenna systems and signal processing technologies designed to detect the incredibly weak signals that would arrive from spacecraft near other star systems. These improvements benefit all deep space missions, enabling more detailed scientific data return from spacecraft throughout our solar system, while laying the groundwork for interstellar communication capabilities. The artificial intelligence systems being developed for autonomous interstellar operation represent another frontier where interstellar mission requirements are driving broader technological advancement. Spacecraft traveling to other star systems must be capable of independent decision-making across timescales ranging from microseconds to decades. They need to navigate around obstacles, respond to equipment failures, prioritize scientific observations, and adapt to unexpected discoveries, all without guidance from Earth. These autonomous systems must be robust enough to operate for decades, without updates or maintenance, while remaining flexible enough to handle situations that mission planners never anticipated. The development of such long-term autonomous capabilities is advancing artificial intelligence research in areas that benefit applications far beyond space exploration, from autonomous vehicles to industrial process control. The data storage and processing requirements for interstellar missions are equally demanding. Spacecraft may need to store years' worth of observations and measurements before opportunities arise to transmit data back to Earth. The storage systems must be resistant to radiation damage, capable of error correction over extended time periods, and efficient enough to operate within the power constraints of deep space missions. Recent advances in quantum computing and quantum communication technologies offer intriguing possibilities for interstellar missions. Quantum sensors could provide unprecedented sensitivity for detecting magnetic fields, gravitational variations, and other subtle phenomena around distant worlds. Quantum communication systems might enable secure data transmission across interstellar distances while providing natural error correction capabilities. The selection of scientific instruments for interstellar missions involves complex trade-offs between capability, mass, power consumption, and reliability. Every gram of scientific equipment must justify its inclusion through the unique data it can provide about distant worlds. Mission planners are developing sophisticated optimization algorithms to select instrument packages that maximize scientific return while meeting the severe constraints imposed by interstellar travel requirements. Spectroscopic instruments capable of analyzing atmospheric compositions from great distances are being miniaturized and optimized for the specific challenges of interstellar observation. These systems must be sensitive enough to detect trace gases that might indicate biological activity, while being robust enough to operate reliably for decades in the harsh environment of interstellar space. Imaging systems for interstellar missions face the challenge of providing useful resolution of planetary surfaces and atmospheric features from spacecraft that may never approach closer than several astronomical units from their targets. Advanced image processing algorithms and synthetic aperture techniques are being developed to extract maximum information from the limited photons that such distant observations would provide. The power systems required for interstellar missions represent another area where extreme requirements are driving technological innovation. Spacecraft traveling between star systems cannot rely on solar panels once they move far from their target stars, and they must operate for decades or centuries without maintenance. These constraints are spurring development of advanced nuclear power systems, radioisotope thermoelectric generators, and potentially fusion-powered electrical generation systems. Thermal management becomes critically important for interstellar spacecraft, which must dissipate waste heat in the near vacuum of interstellar space while maintaining operational temperatures for sensitive electronics and scientific instruments. Advanced radiator designs and thermal control systems are being developed to handle these challenging requirements efficiently. The navigation and attitude control systems for interstellar missions must maintain precise pointing and trajectory control across distances where Earth appears as little more than a pale dot against the cosmic background. Star trackers, inertial guidance systems, and autonomous navigation algorithms are being advanced to meet these unprecedented accuracy requirements over extended mission durations. As these various technologies mature and converge, the prospect of practical interstellar missions transitions from science fiction toward engineering reality. The combination of advanced propulsion systems, miniaturized instruments, autonomous control systems, and improved communication technologies is creating a technological foundation that could support humanity's first journeys to other star systems within the coming decades. The timeline for these developments suggests that the first interstellar missions might be launched within the next 20 to 30 years, though they would still require decades or centuries to reach their destinations. This timeline means that decisions being made today about research priorities, funding allocations, and international cooperation will directly determine whether humanity becomes an interstellar species within the lifetimes of people alive today. The cumulative effect of these technological advances extends far beyond their applications to interstellar travel. The innovations being driven by the extreme requirements of interstellar missions are finding applications in fields ranging from terrestrial energy production to medical devices, from autonomous systems to advanced materials manufacturing. The pursuit of interstellar travel is catalyzing a wave of technological development that benefits human civilization across multiple domains. As you contemplate these remarkable technological developments, consider that we are witnessing the emergence of capabilities that will define humanity's cosmic future. The fusion reactors, light sails, miniaturized spacecraft, and autonomous systems being developed today may carry our descendants across the cosmic ocean to distant shores we can only imagine. The engineering challenges that seem insurmountable today are yielding to human ingenuity and determination, bringing the stars within reach of human exploration. The next phase of our cosmic journey will reveal how these technologies might be integrated into comprehensive mission architectures capable of carrying human knowledge and perhaps human presence across the vast distances that separate us from other worlds. The dream of interstellar travel is transforming from fantasy into engineering challenge, and the solutions emerging from laboratories around the world suggest that the age of interstellar exploration may be closer than we dare to hope. The technological convergence we're witnessing today represents more than just incremental improvements in space technology. It signals a fundamental transformation in how we approach the challenge of crossing interstellar space, moving from theoretical speculation toward practical mission planning that could define humanity's next chapter among the stars. Perhaps the most profound realization emerging from current research is that interstellar travel may not require a single revolutionary breakthrough, but rather the careful orchestration of multiple advanced technologies working in harmony. The fusion propulsion systems under development don't need to achieve perfect efficiency. The light sails don't need to be completely indestructible. And the miniaturized spacecraft don't need to carry every conceivable scientific instrument. Instead, each component needs to be good enough to contribute to an integrated system capable of crossing the cosmic gulf between star systems. This system's approach to interstellar exploration is revealing mission architectures that seemed impossible when each technology was considered in isolation. Hybrid propulsion concepts combine the steady acceleration of fusion drives with the high-speed capabilities of laser-powered light sails. Multi-stage mission profiles might use conventional propulsion to reach the outer solar system, then deploy light sails for final acceleration toward target stars. These integrated approaches are making interstellar missions more feasible while reducing the performance requirements for any single technology. The development of interstellar mission architectures is also driving advances in space-based manufacturing and assembly. The massive structures required for some interstellar propulsion concepts cannot practically be launched from Earth's surface. Instead, they would need to be constructed in space using materials mined from asteroids or manufactured in zero-gravity environments. This requirement is accelerating research into space-based industrial capabilities that could transform human presence throughout the solar system. Orbital shipyards capable of assembling interstellar spacecraft represent a natural evolution of the space-based manufacturing capabilities being developed for lunar and asteroid mining operations. These facilities would need to handle exotic materials, precision assembly of delicate components, and integration of systems designed to operate for decades in the harsh environment of interstellar space. The technologies being developed for such facilities are finding immediate applications in Earth orbit manufacturing and deep space mission preparation. The scale of interstellar missions is also driving innovations in project management and international cooperation. No single organization or nation possesses the resources needed to mount serious interstellar exploration efforts. The collaborative frameworks being developed for these missions are creating new models for international scientific cooperation that extend far beyond traditional space exploration partnerships. Long-term institutional commitments spanning multiple decades require governance structures that can survive changes in political leadership, economic conditions, and social priorities. The frameworks being developed for interstellar missions are pioneering approaches to multi-generational project management that could transform how humanity approaches other long-term challenges. From climate change mitigation to infrastructure development, the financial models for interstellar missions are evolving beyond traditional government funding toward hybrid approaches that combine public investment with private capital and international cost-sharing agreements. The enormous upfront costs are being distributed across multiple stakeholders and extended timeframes in ways that make these ambitious projects economically feasible without overwhelming any single funding source. Recent economic analyses suggest that the total cost of first-generation interstellar missions, while substantial, represents a manageable fraction of global space expenditures when distributed across the international community and extended over realistic development timelines. The economic benefits from technological spin-offs and industrial development could offset significant portions of the direct mission costs. The scientific return from interstellar missions extends far beyond the immediate data collected at target destinations. The technologies developed for interstellar travel are advancing multiple fields of physics and engineering simultaneously. The long journey times provide opportunities for extended observations of interstellar space itself, revealing insights about cosmic ray propagation, interstellar magnetic fields, and the structure of the local galactic environment. Interstellar missions would also serve as testbeds for technologies needed for more ambitious space exploration efforts within our own solar system. The autonomous systems, advanced propulsion, and long-duration operation capabilities required for interstellar travel would enable more capable missions to the outer planets, Kuiper Belt objects, and eventually the Oort clouds surrounding our solar system. The data transmission challenges inherent in interstellar missions are driving advances in communication technologies that benefit all deep space exploration efforts. The ultra-sensitive receivers and high-power transmitters being developed for interstellar communication will enable more detailed scientific observations from spacecraft throughout the solar system while providing the foundation for an interstellar communication network. As we contemplate the prospect of receiving signals from spacecraft near other star systems, we must also consider the profound impact such communications would have on human consciousness and culture. The first images of another Earth-like world, the first spectroscopic analysis of an alien atmosphere, the first detection of chemical signatures that might indicate life beyond our solar system would represent moments of discovery that transform our understanding of our place in the cosmic community. The protocols being developed for handling such discoveries reflect the extraordinary significance of potential findings. International committees are establishing procedures for verifying, analyzing, and announcing discoveries that could fundamentally alter human understanding of life in the universe. These protocols must balance scientific rigor with public communication, ensuring that extraordinary claims are supported by extraordinary evidence while sharing the wonder of discovery with all humanity. The psychological preparation for interstellar exploration extends beyond mission planning toward broader questions about human identity and cosmic citizenship. The images and data returned by interstellar missions will provide humanity with its first detailed look at worlds beyond our solar system, potentially revealing landscapes and phenomena that challenge our understanding of planetary formation and evolution. The cultural impact of interstellar exploration may prove as significant as its scientific contributions. The shared human endeavor of reaching toward other star systems could provide a unifying purpose that transcends national boundaries and cultural differences. The long timescales involved in interstellar missions require sustained cooperation across generations, fostering the kind of long-term thinking that could benefit humanity's approach to other global challenges. Educational initiatives associated with interstellar missions are already inspiring new generations of scientists, engineers, and explorers. The technical challenges of interstellar travel provide compelling contexts for teaching advanced physics, engineering, and mathematics, while connecting abstract concepts to humanity's greatest adventure. Students working on interstellar mission concepts today may become the engineers and scientists who make such missions reality. The artistic and philosophical dimensions of interstellar exploration are inspiring new forms of creative expression that help humanity process the implications of becoming an interstellar species. Writers, artists, and musicians are exploring themes of cosmic exploration, technological transcendence, and human expansion beyond Earth in ways that help society prepare emotionally and culturally for the realities of interstellar travel. The environmental considerations of interstellar missions are also driving innovations in sustainable technology development. The closed-loop life support systems, ultra-efficient power generation, and minimal waste production required for interstellar travel are advancing technologies that could improve sustainability on Earth. The perspective gained from planning to become an interstellar species may help humanity develop the long-term thinking needed to address environmental challenges on our home planet. Recent developments in astrobiology are refining our understanding of what to look for when searching for life on distant worlds. The detection techniques being developed for interstellar missions must be sensitive enough to identify biosignatures from great distances, while being robust enough to distinguish genuine biological signals from non-biological phenomena that could mimic life's chemical signatures. The possibility of discovering microbial life on exoplanets raises profound questions about contamination protocols and planetary protection measures for interstellar missions. Unlike solar system exploration, where spacecraft can potentially return samples to Earth, interstellar missions represent one-way journeys that must carry all necessary analysis capabilities with them. The sterilization and contamination prevention protocols being developed for these missions are advancing planetary protection science across all space exploration activities. The search for technological signatures of advanced civilizations adds another dimension to interstellar mission planning. Spacecraft approaching other star systems would be ideally positioned to search for signs of technology, from artificial illumination patterns on planetary night sides to megastructures that might indicate highly advanced civilizations. The instruments and analysis techniques being developed for such searches are advancing the field of astroengineering and expanding our concepts of what to look for when searching for intelligence beyond Earth. As interstellar mission concepts mature from theoretical studies toward engineering development programs, we're witnessing the emergence of a new era in human space exploration. The technologies being developed today could enable the first robotic emissaries to depart for other star systems within the next few decades, carrying human knowledge and curiosity across the cosmic ocean toward distant worlds that have waited billions of years for visitors from Earth. The challenges that remain are substantial, requiring continued advances across multiple fields of science and engineering. Yet the progress being made suggests that these challenges are not insurmountable barriers, but rather engineering problems that yield to sustained effort and international cooperation. The convergence of advanced propulsion, miniaturized instruments, autonomous systems, and improved communication technologies is creating possibilities that seemed like pure fantasy just generations ago. The next phase of human cosmic evolution may unfold more rapidly than we expect, as exponential advances in key technologies compress development timelines and reduce costs. The intersection of artificial intelligence, advanced materials science, fusion energy, and precision manufacturing could accelerate interstellar mission capabilities beyond current projections, bringing the age of interstellar exploration closer than our most optimistic estimates suggest. As you rest here contemplating these cosmic possibilities, consider that you are living at the threshold of humanity's transformation from a single planet species to an interstellar civilization. The decisions being made today about research priorities, international cooperation, and long-term commitment to space exploration will determine whether future generations inherit a universe filled with reachable destinations or remain forever bound to the single world that gave birth to human consciousness. The stars that shine above you tonight represent more than distant suns. They are beacons calling humanity toward a future among the cosmic community. Destinations that may one day welcome visitors carrying the story of Earth across the vast ocean of space. The technologies being developed in laboratories around the world may soon transform these distant lights from unreachable objects of wonder into accessible worlds of discovery and exploration. The timeline for humanity's first interstellar missions is beginning to crystallize as research programs around the world converge on similar conclusions about technological readiness and mission feasibility. Recent assessments suggest that we may be closer to launching our first robotic ambassadors to other star systems than many realize, with prototype technologies already demonstrating capabilities that seemed impossible just years ago. The fusion propulsion systems currently under development represent perhaps the most mature pathway to practical interstellar travel. Unlike the massive tokamak reactors being built for terrestrial power generation, these space-based fusion systems focus on compact, efficient designs optimized for the unique requirements of spacecraft propulsion. The magnetic confinement approaches being tested in laboratories worldwide are achieving plasma densities and temperatures that approach the thresholds needed for sustained fusion reactions in space environments. What makes these developments particularly encouraging is that fusion propulsion doesn't require perfect efficiency to enable interstellar missions. Even relatively modest fusion systems could accelerate spacecraft to velocities that reduce interstellar journey times from tens of thousands of years to mere centuries. While centuries still seem daunting from our current perspective, they represent timeframes that human institutions have successfully sustained throughout history. The great cathedrals of Europe required centuries to complete, and their builders understood they were working for future generations who would see their visions fulfilled. The compact reactor designs being pursued by research institutions combine magnetic confinement with innovative fuel cycles that maximize energy output while minimizing reactor mass. These systems must operate reliably for decades without maintenance, withstanding radiation levels and temperature extremes that would destroy conventional technology. The materials science breakthroughs required for such reactors are advancing rapidly, driven by applications ranging from terrestrial fusion power to advanced space propulsion. Recent theoretical studies suggest that fusion-powered spacecraft could achieve exhaust velocities approaching 10% of light speed, enabling them to reach significant fractions of that velocity through efficient staging and fuel management strategies. A spacecraft capable of reaching 5% of light speed could complete the journey to Proxima Centauri in less than a century, making interstellar exploration feasible within institutional planning horizons that humans have successfully managed before. The development of these propulsion systems is being accelerated by advances in computational modeling that allow researchers to simulate fusion reactions and plasma behavior with unprecedented accuracy. These simulations are revealing design optimizations that could dramatically improve the performance and reliability of space-based fusion reactors while reducing their complexity and mass. The virtual testing capabilities now available to fusion researchers are compressing development timelines and reducing the costs associated with physical prototyping. Meanwhile, the laser propulsion concepts pioneered by the breakthrough Starshot initiative continue to evolve as researchers address the fundamental challenges that initially seemed insurmountable. The atmospheric compensation systems needed to maintain laser beam coherence through Earth's atmosphere are benefiting from advances in adaptive optics originally developed for astronomical telescopes. These systems can now correct for atmospheric disturbances with speeds and accuracy that make ground-based laser propulsion theoretically feasible. The cost reductions needed to make laser propulsion economically viable are following trajectories similar to those observed in solar panel and computer processor development. Laser efficiency improvements and manufacturing scale-up are driving costs down exponentially, bringing the economic requirements for interstellar laser propulsion within reach of international collaborative funding models. The massive laser arrays required for such missions could be constructed incrementally, allowing costs to be distributed across multiple years and funding sources. Recent breakthroughs in laser technology have demonstrated power scaling approaches that could achieve the enormous optical power requirements for interstellar missions, without requiring revolutionary advances in fundamental physics. Coherent beam combining techniques allow thousands of individual lasers to work together as a single focused system, while adaptive optics maintain beam quality across the entire array. These technologies are already being deployed for industrial and defense applications, providing a mature technological foundation for interstellar propulsion systems. The spacecraft being designed for laser propulsion missions continue to benefit from the relentless miniaturization of electronic components and scientific instruments. Modern sensors can perform sophisticated chemical analyses using devices smaller than coins, while communication systems that once required room-sized equipment now fit into packages weighing less than paper clips. This extreme miniaturization enables mission concepts that would have been impossible with earlier technologies, allowing comprehensive scientific investigations using spacecraft that weigh less than insects. The light sails required for laser propulsion are approaching the theoretical limits of materials science, incorporating substances and structures that exist at the boundary between engineering and physics. These ultra-thin membranes combine graphene layers with quantum dot coatings and metamaterial structures to achieve properties that seem almost magical in their combination of lightness, strength, and optical performance. The manufacturing techniques being developed for these materials are advancing nanotechnology and precision fabrication across multiple industries. Testing programs for interstellar technologies are expanding rapidly as space-based platforms become more accessible and affordable. Small demonstration spacecraft are being deployed to validate critical technologies in the harsh environment of space, providing crucial performance data under conditions that cannot be replicated in terrestrial laboratories. These tests are revealing both challenges and opportunities that refine mission designs and improve success probabilities for full-scale interstellar missions. The international cooperation frameworks being developed for interstellar missions represent innovations in global collaboration that extend far beyond space exploration. The multi-generational commitments required for interstellar missions are driving the creation of institutional structures designed to maintain continuity across political changes and economic fluctuations. These governance models could serve as templates for other long-term global challenges that require sustained international cooperation. Funding models for interstellar missions are evolving beyond traditional government appropriations toward hybrid approaches that combine public investment with private capital and innovative financing mechanisms. The total costs, while substantial, become manageable when distributed across international partnerships and extended development timelines. Recent economic analyses suggest that interstellar missions could be funded at levels comparable to major infrastructure projects or scientific facilities, making them feasible within existing institutional capabilities. The scientific instruments being developed for interstellar missions represent marvels of miniaturization that compress laboratory-quality analysis capabilities into packages measured in grams. Spectrometers capable of identifying atmospheric gases, cameras with resolution sufficient to detect planetary surface features, and magnetometers sensitive enough to map magnetic field structures around distant worlds are all being designed to operate reliably for decades in the extreme conditions of interstellar space. Advanced artificial intelligence systems are being developed to provide the autonomous decision-making capabilities that interstellar spacecraft will require during their decades-long journeys. These systems must be robust enough to operate without updates or maintenance while remaining flexible enough to adapt to unexpected discoveries and equipment failures. The autonomous capabilities being developed for interstellar missions are advancing artificial intelligence research in areas that benefit applications throughout human society. Communication systems for interstellar missions are pushing the boundaries of what's possible with electromagnetic radiation across cosmic distances. The ultra-sensitive receivers and high-power transmitters required for interstellar communication will enable more detailed scientific observations from spacecraft throughout the solar system, while providing the technological foundation for an eventual interstellar communication network. These advances are improving deep space communication capabilities across all space exploration programs. The data storage and processing requirements for interstellar missions are driving innovations in long-term information preservation and autonomous data management. Spacecraft may need to store years of observations before transmission opportunities arise, requiring storage systems that can maintain data integrity across decades while operating in radiation-rich environments. The error correction and data compression techniques being developed for these missions are advancing information technology across multiple applications. Navigation and attitude control systems for interstellar missions must maintain precise pointing and trajectory control across distances where Earth appears as little more than a faint star. The star tracking systems, inertial guidance technologies, and autonomous navigation algorithms being developed for these missions are achieving accuracy levels that seemed impossible with earlier technologies. These advances are improving precision navigation capabilities for all deep space missions. Thermal management becomes critically important for interstellar spacecraft operating in the near vacuum of space between star systems. Advanced radiator designs and thermal control systems are being developed to dissipate waste heat efficiently while maintaining operational temperatures for sensitive electronics and scientific instruments. The thermal management solutions being created for interstellar missions are finding applications in terrestrial electronics and industrial processes. Power systems for interstellar missions must provide reliable electrical generation for decades without maintenance or refueling. Advanced radioisotope thermoelectric generators, compact nuclear reactors, and potentially fusion-powered electrical systems are being developed to meet these demanding requirements. The long-duration power technologies being created for interstellar missions are advancing energy storage and generation capabilities across multiple applications. The convergence of these various technologies is revealing mission architectures that make interstellar exploration increasingly feasible. Hybrid approaches that combine multiple propulsion concepts, distributed spacecraft designs that provide redundancy and comprehensive coverage, and staged mission profiles that optimize performance across different phases of interstellar journeys are creating pathways to other star systems that seemed impossible when individual technologies were considered in isolation. Recent mission studies suggest that the first interstellar probes could be launched within the next 2 to 3 decades, carrying human knowledge and curiosity across the cosmic ocean toward worlds that have waited billions of years for visitors. These pioneering missions would represent humanity's first steps beyond the solar system, establishing communication links across interstellar distances and providing the experience needed for more ambitious future explorations. The selection of target destinations for early interstellar missions involves complex considerations of scientific interest, mission feasibility, and symbolic significance. While Proxima Centauri B remains the most obvious candidate due to its proximity and potential habitability, other recently discovered worlds offer compelling alternatives that might justify longer journey times or more challenging mission requirements. The diversity of exoplanets now known to exist provides mission planners with an unprecedented menu of potential destinations. As these technological capabilities mature and mission concepts crystallize into engineering development programs, we find ourselves approaching a historic threshold in human development. The transformation from a single planet species confined to one star system toward an interstellar civilization capable of exploring distant worlds represents an evolutionary leap comparable to the emergence of life from the oceans onto land billions of years ago. The challenges that remain are substantial but not insurmountable, requiring continued advances in propulsion technology, autonomous systems, and international cooperation. Yet the progress being made across multiple fields suggests that these challenges are yielding to sustained scientific effort and engineering innovation. The convergence of advanced materials, artificial intelligence, fusion energy, and precision manufacturing is creating possibilities that compress development timelines and reduce costs beyond current projections. The psychological and cultural preparation for becoming an interstellar species may prove as important as the technological developments that make such missions possible. The images and data that will eventually arrive from spacecraft near other star systems will provide humanity with its first detailed observations of alien worlds, potentially revealing phenomena that challenge our understanding of planetary formation, atmospheric evolution, and perhaps even the prevalence of life throughout the galaxy. Educational initiatives associated with interstellar mission development are already inspiring new generations of scientists and engineers who will inherit the responsibility for humanity's expansion beyond the solar system. The technical challenges of interstellar travel provide compelling contexts for advanced education in physics, engineering, and mathematics, while connecting abstract concepts to humanity's greatest adventure among the stars. The environmental perspective gained from planning interstellar missions is also contributing to more sustainable approaches to technology development and resource utilization. The closed-loop systems, ultra-efficient power generation, and minimal waste production required for interstellar travel are advancing technologies that could improve sustainability on Earth while preparing humanity for the resource constraints of deep space exploration. As we stand at this remarkable juncture in human history, with the technological foundations for interstellar travel taking shape in laboratories around the world, we must recognize that the decisions being made today will determine whether future generations inherit a universe filled with accessible destinations, or remain forever confined to the single world that gave birth to human consciousness. The investments being made in fusion research, advanced materials, artificial intelligence, and international cooperation are laying the groundwork for humanity's cosmic future. The stars that shine in tonight's sky represent more than distant objects of scientific curiosity. They are potential destinations for human exploration, worlds that may harbor their own stories of planetary evolution and perhaps even life itself. The technologies being developed in research facilities across the globe are transforming these distant lights from unreachable points of wonder into accessible worlds of discovery and understanding. The timeline for humanity's first tentative steps beyond our solar system is becoming increasingly clear as multiple technological pathways converge toward practical interstellar missions. Recent assessments by space agencies and research institutions worldwide suggest we may witness the launch of our first robotic ambassadors to other star systems within the next 20 to 40 years, carrying with them not just scientific instruments, but the hopes and dreams of an entire species reaching toward the cosmic community. What makes this prospect particularly remarkable is that we're not waiting for a single revolutionary breakthrough to make interstellar travel possible. Instead, we're witnessing the careful orchestration of incremental advances across multiple fields, each building upon the others to create capabilities that seemed like pure fantasy just decades ago. The fusion reactors being tested in laboratories are achieving plasma temperatures and confinement times that approach the thresholds needed for space-based propulsion. The materials being developed for light sails are approaching theoretical limits of strength and lightness. The miniaturized instruments being designed for interstellar probes can perform analyses that once required room-sized equipment. This convergence is happening faster than many experts anticipated, driven by exponential improvements in computing power, materials science, and manufacturing precision. The artificial intelligence systems needed to guide spacecraft across interstellar distances are benefiting from machine learning advances that compress decades of development into years. The communication technologies required to maintain contact across light years are advancing alongside improvements in laser technology and signal processing that make interstellar data transmission increasingly feasible. Recent breakthroughs in fusion plasma physics have demonstrated sustained reactions under conditions similar to what space-based reactors would encounter. These achievements represent more than laboratory curiosities. They're stepping stones toward propulsion systems that could accelerate spacecraft to significant fractions of light speed. The magnetic confinement techniques being perfected in terrestrial fusion research translate directly to spacecraft applications, where compact reactors must operate reliably for decades without maintenance or refueling opportunities. The economic models supporting these ambitious projects are evolving beyond traditional government funding toward innovative partnerships that distribute costs and risks across multiple nations and institutions. The total investment required for first-generation interstellar missions, while substantial, becomes manageable when shared among international collaborators and extended across realistic development timelines. Recent economic analyses suggest that interstellar exploration programs could be funded at levels comparable to major particle accelerator projects or space telescope programs, making them achievable within existing institutional frameworks. Perhaps most encouraging is the growing recognition that interstellar missions don't require perfect technology to succeed. Early missions can achieve transformative scientific results, even if they represent compromised solutions that balance performance against reliability and cost. A spacecraft capable of reaching 5% of light speed could complete the journey to nearby star systems within a human lifetime, while missions achieving even lower velocities could provide unprecedented insights into interstellar space and distant planetary systems within institutional planning horizons that human civilization has successfully managed before. The scientific return from interstellar missions extends far beyond the data collected at target destinations. The decades-long journeys themselves would provide unprecedented opportunities to study the interstellar medium, cosmic ray propagation, and magnetic field structures throughout the local galactic environment. These observations would advance our understanding of stellar formation, galactic evolution, and the physical processes that shape the cosmic web on scales impossible to study from within our solar system. The technological spin-offs from interstellar mission development are already benefiting applications throughout human society. The advanced materials being created for light sails are finding uses in electronics, aerospace, and energy storage. The autonomous systems being developed for decades-long space missions are improving robotic capabilities across industries from manufacturing to exploration. The precision pointing and communication technologies required for interstellar missions are enhancing everything from satellite navigation to deep space astronomy. International cooperation frameworks being developed for interstellar missions are pioneering new approaches to global collaboration that could serve as models for other long-term challenges facing human civilization. The institutional structures needed to maintain continuity across multiple decades of mission development and execution are creating governance models designed to survive political changes, economic fluctuations, and shifting social priorities. These frameworks represent innovations in international cooperation that extend far beyond space exploration. The psychological preparation for receiving data from interstellar missions is already beginning as scientists and educators work to help society understand the profound implications of becoming an interstellar species. The first images of Earth-like worlds around other stars, the first spectroscopic analyses of alien atmospheres, and the first measurements of magnetic fields and radiation environments around distant planets will represent moments of discovery that transform human understanding of our place in the cosmic community. Educational initiatives associated with interstellar mission development are inspiring students worldwide to pursue careers in science and engineering. The technical challenges of crossing interstellar space provide compelling context for teaching advanced physics, mathematics, and engineering, while connecting abstract concepts to humanity's greatest adventure. Young people working on interstellar mission concepts today may become the engineers and scientists who make such missions reality within their own lifetimes. The cultural impact of interstellar exploration may prove as significant as its scientific contributions. The shared human endeavor of reaching toward other star systems could provide a unifying purpose that transcends national boundaries and cultural differences. The long timescales inherent in interstellar missions require sustained cooperation across generations, fostering the kind of long-term thinking that could benefit humanity's approach to climate change, resource management, and other global challenges requiring multi-generational solutions. Recent developments in astrobiology are refining our understanding of biosignatures and the techniques needed to detect life from interstellar distances. The instruments being designed for interstellar missions must be sensitive enough to identify chemical signatures of biological processes, while being robust enough to distinguish genuine biosignatures from non-biological phenomena that could mimic life's chemical fingerprints. These advances are improving our ability to search for life throughout the cosmos while preparing us for the possibility of discovering that we are not alone. The possibility of finding evidence for technological civilizations adds another dimension to interstellar mission planning. Spacecraft approaching other star systems would be ideally positioned to search for signs of advanced technology, from artificial illumination patterns on planetary night sides to megastructures that might indicate highly developed civilizations. The search techniques being developed for such investigations are expanding our concepts of what to look for when seeking intelligence beyond Earth. Communication protocols for interstellar missions must account for the years-long delays inherent in transmitting data across light years of space. The data compression and error correction techniques being developed for these missions are advancing information technology while preparing humanity for the unique challenges of maintaining communication links across interstellar distances. These systems must operate autonomously for years while preserving data integrity under conditions that would destroy conventional electronics. The navigation challenges faced by interstellar spacecraft are driving advances in autonomous guidance systems that must maintain precise trajectories across distances where Earth appears as little more than a faint star. The stellar reference systems and inertial guidance technologies being developed for these missions are achieving accuracy levels that seemed impossible with earlier technologies. These advances are improving precision navigation capabilities for all deep space missions, while laying the groundwork for an eventual interstellar transportation network. Thermal management systems for interstellar spacecraft must dissipate waste heat efficiently while operating in the near vacuum of space between star systems. The radiator designs and thermal control technologies being developed for these missions are finding applications in terrestrial electronics and industrial processes, while solving the unique challenges of maintaining operational temperatures during decades-long journeys through interstellar space. Power generation systems for interstellar missions must provide reliable electrical output for decades without maintenance, refueling, or replacement. The advanced nuclear systems, improved radioisotope generators, and potentially fusion-powered electrical systems being developed for these missions are advancing long-duration power technologies across multiple applications while solving the specific challenges of deep space energy requirements. The integration of these various technologies into comprehensive mission architectures is revealing pathways to interstellar exploration that seemed impossible when individual components were considered separately. Hybrid propulsion approaches that combine fusion acceleration with light sail technology, distributed spacecraft designs that provide redundancy through multiple small probes, and staged mission profiles that optimize performance across different journey phases are creating realistic approaches to crossing the cosmic ocean. Mission planners are developing increasingly sophisticated strategies for maximizing scientific return from interstellar missions while minimizing risks and costs. These approaches might involve multiple spacecraft launched toward different target systems, providing comparative data about various types of planetary systems and stellar environments. Such distributed exploration programs could transform our understanding of planetary formation, atmospheric evolution, and the prevalence of life throughout the galaxy. The selection of instruments for interstellar missions involves complex optimization algorithms that balance scientific capability against mass, power consumption, and reliability constraints. Every component must justify its inclusion through the unique data it can provide about distant worlds, while meeting the severe requirements imposed by decades of operation in the harsh environment of interstellar space. These optimization techniques are advancing mission design capabilities across all space exploration programs. Recent studies suggest that interstellar missions could be implemented using evolutionary approaches that begin with less ambitious objectives and gradually build toward more comprehensive exploration capabilities. Early missions might focus on reaching the outer boundaries of our solar system and beginning the journey toward interstellar space, providing crucial experience with long-duration autonomous operations while testing technologies needed for more ambitious future missions. The data analysis challenges posed by interstellar missions are driving advances in autonomous scientific reasoning and pattern recognition. Spacecraft must be capable of identifying interesting phenomena, prioritizing observations, and adapting to unexpected discoveries without guidance from Earth. The artificial intelligence systems being developed for these missions are advancing machine learning research in areas that benefit applications throughout human society. Contamination prevention protocols for interstellar missions must ensure that Earth-based microorganisms don't interfere with the search for indigenous life on distant worlds. The sterilization techniques and planetary protection measures being developed for these missions are advancing our understanding of extremophile biology, while establishing procedures that could prevent contamination of alien ecosystems by terrestrial life forms. As these various technological streams converge toward practical interstellar mission capabilities, we find ourselves approaching a threshold that will transform humanity from a single planet species into an interstellar civilization. The decisions being made today about research priorities, international cooperation, and long-term technological development will determine whether future generations inherit a universe filled with accessible destinations or remain forever confined to the solar system that gave birth to human consciousness. The stars visible in tonight's sky represent more than distant suns burning in the cosmic darkness. They are beacons calling humanity toward a future among the galactic community. Destinations that may welcome visitors carrying the story of Earth across the vast ocean of space. The technologies taking shape in laboratories around the world are transforming these distant lights from objects of wonder into accessible worlds of discovery and exploration. The timeline for humanity's transformation into an interstellar species may unfold more rapidly than we expect, as exponential advances in key technologies compress development schedules and reduce costs beyond current projections. The intersection of artificial intelligence, advanced materials, fusion energy, and precision manufacturing could accelerate interstellar capabilities in ways that surprise even the most optimistic researchers working in these fields today. As you drift deeper into contemplation of these cosmic possibilities, consider that you are witnessing the emergence of capabilities that will define humanity's place among the stars for generations to come. The fusion reactors, light sails, miniaturized spacecraft, and autonomous systems being developed today may carry our knowledge and perhaps our presence across the cosmic gulf to shores we can only imagine. The engineering challenges that seem formidable today are yielding to human creativity and determination, bringing the age of interstellar exploration within reach of human ambition. The profound implications of becoming an interstellar civilization extend far beyond the technological achievements required to cross the cosmic ocean. As we stand on the threshold of this transformation, we must consider how the very act of reaching toward other worlds is already changing our understanding of what it means to be human in a universe that may harbor countless other forms of consciousness and complexity. The search for potentially habitable exoplanets has revealed a cosmos far richer and more diverse than our ancestors could have imagined. Each new discovery adds another chapter to the growing catalogue of worlds that orbit distant stars, worlds where liquid water might flow, where atmospheric chemistry might support the intricate dance of molecules that gives rise to life as we understand it. These discoveries are not mere additions to astronomical databases. They represent potential destinations for future human exploration, worlds that might one day witness the arrival of visitors from Earth, carrying the accumulated knowledge and dreams of our entire species. The diversity of planetary systems now known to exist challenges our assumptions about how worlds form and evolve. We have found planets orbiting binary star systems where two suns dance across alien skies. We have discovered worlds where diamond rain might fall from atmospheric pressures that would crush any terrestrial life form. We have identified planets where the very concept of seasons would be meaningless because one hemisphere experiences eternal day while the other knows only perpetual night. Each discovery expands our understanding of the possible, revealing that the universe is far more creative in its planetary architectures than our Earth-centered perspective initially suggested. Recent advances in atmospheric spectroscopy are beginning to reveal the chemical compositions of distant worlds, allowing us to peer into alien atmospheres and search for the molecular signatures that might indicate biological processes. The detection of water vapor, oxygen, methane, and other compounds in exoplanet atmospheres represents our first tentative steps toward understanding the chemistry of worlds we may never visit directly, but can study from across the cosmic distances that separate us from them. The James Webb Space Telescope and other advanced observatories are providing unprecedented detail about the atmospheric compositions and surface conditions of nearby exoplanets. These observations are revealing worlds with atmospheric pressures and temperatures that span enormous ranges, from planets where surface rocks would glow red hot to frozen worlds where even the thinnest atmospheres have collapsed into surface ice. The variety of conditions we are discovering suggests that the universe contains environments far more extreme and diverse than anything found within our own solar system. The characterization of potentially habitable worlds requires sophisticated modeling techniques that combine atmospheric chemistry, planetary physics, and climate science to understand how different worlds might support liquid water and the complex chemistry associated with life. These models are revealing that habitability depends on far more than simple distance from a host star, incorporating factors such as atmospheric composition, magnetic field strength, geological activity, and the radiation environment created by stellar activity. Recent studies suggest that some worlds initially dismissed as inhospitable might actually harbor conditions suitable for life in regions we hadn't previously considered. Tidally locked planets, where one side permanently faces their star while the other experiences eternal darkness, might maintain habitable zones along the terminator line where day and night meet. Subsurface oceans beneath planetary ice shells could provide protected environments where life might flourish despite hostile surface conditions. Atmospheric circulation patterns could distribute heat so efficiently that even worlds with extreme day-night temperature differences might maintain regions where liquid water could persist. The search for biosignatures in exoplanet atmospheres represents one of the most ambitious scientific endeavors ever undertaken, requiring instruments sensitive enough to detect trace gases from distances measured in light years, while sophisticated enough to distinguish genuine biological signatures from geological or atmospheric processes that might produce similar chemical fingerprints. The techniques being developed for this search are advancing spectroscopic analysis across multiple fields while preparing humanity for the possibility that we might detect clear evidence of life beyond our solar system within the coming decades. The discovery of life beyond Earth, even in microbial form, would represent one of the most profound moments in human history, fundamentally altering our understanding of biology, evolution, and our place within the cosmic community. The protocols being developed for announcing and analyzing such discoveries reflect the extraordinary significance of potential findings, requiring multiple independent confirmations and extensive peer review before any claims about extraterrestrial life could be accepted by the scientific community. The implications of finding life elsewhere extend far beyond academic curiosity toward fundamental questions about the nature of consciousness, intelligence, and technological development. If life has emerged independently on multiple worlds within our local galactic neighborhood, it suggests that the universe might be teeming with biological activity on scales we can barely comprehend. Such a discovery would transform astrobiology from a speculative field into an observational science with countless worlds to study and understand. The possibility of discovering technological signatures alongside biological ones adds another layer of complexity to our search for life beyond Earth. Advanced civilizations might leave detectable traces of their presence through artificial illumination patterns, atmospheric pollution, megastructures, or directed energy transmissions. The search techniques being developed for identifying such signatures are expanding our concepts of what constitutes evidence for intelligence, while preparing us for the possibility that some of the worlds we study might harbor civilizations with technologies far more advanced than our own. The psychological preparation for potential contact with extraterrestrial intelligence, whether biological or technological, requires careful consideration of how such discoveries might affect human society, religion, philosophy, and our fundamental understanding of our cosmic significance. The frameworks being developed for processing and communicating such discoveries must balance scientific rigor with public education, ensuring that extraordinary claims are supported by extraordinary evidence while sharing the wonder of discovery with all humanity. The development of interstellar communication protocols extends beyond the technical challenges of transmitting signals across cosmic distances toward deeper questions about how different forms of intelligence might attempt to communicate across the barriers of language, culture, and potentially radically different cognitive architectures. The mathematical and physical principles that seem universal to us might provide common ground for communication, but the actual process of exchanging meaningful information with alien intelligences presents challenges that push the boundaries of linguistics, cognitive science, and information theory. Recent advances in artificial intelligence and machine learning are providing new tools for analyzing potential extraterrestrial signals and identifying patterns that might indicate intelligent origin. These systems can process vast amounts of data from radio telescopes and optical observatories, searching for anomalies that might represent technological signatures, while filtering out the countless natural phenomena that could mimic artificial signals. The pattern recognition capabilities being developed for this search are advancing signal processing technologies across multiple applications, while preparing us for the possibility of detecting clear evidence of technological activity beyond our solar system. The long-term implications of becoming an interstellar species extend toward questions about human evolution, cultural development, and the preservation of knowledge across the enormous timescales involved in crossing interstellar distances. The crews or passengers aboard generation ships traveling to distant star systems would experience cultural evolution during their journeys, potentially arriving at their destinations as societies quite different from those that launch them. The social structures, governance systems, and cultural practices needed to maintain coherent communities during multi-generational voyages represent challenges in sociology and anthropology that complement the technical challenges of interstellar propulsion. The preservation of human knowledge and culture during interstellar journeys requires storage systems and transmission protocols capable of maintaining information integrity across decades or centuries of operation in the harsh environment of deep space. The digital storage technologies being developed for these missions must resist radiation damage, cosmic ray impacts, and the gradual degradation that affects all materials over extended time periods. These systems are advancing data preservation techniques while ensuring that future human settlements on distant worlds retain access to the accumulated knowledge and cultural heritage of Earth-based civilization. The biological challenges of long-duration space travel continue to drive advances in life support systems, radiation shielding, and closed-loop ecological systems that could sustain human populations during interstellar journeys. The development of artificial gravity systems, advanced medical facilities, and psychological support systems for isolated communities represents progress in multiple fields while addressing the unique requirements of maintaining human health and social cohesion during voyages lasting decades or centuries. Recent research into hibernation and suspended animation technologies suggests that future interstellar travelers might spend much of their journey in reduced metabolic states, dramatically decreasing the life support requirements and psychological stresses associated with conscious travel across interstellar distances. These technologies are advancing medical science while offering potential solutions to some of the most challenging aspects of human interstellar travel, though significant technical and ethical questions remain about the long-term effects of extended hibernation on human physiology and consciousness. The terraforming technologies needed to establish human settlements on distant worlds represent another frontier where interstellar exploration drives innovation across multiple fields. The atmospheric engineering, ecological design, and planetary modification techniques being developed for potential use on exoplanets are advancing our understanding of Earth's own climate systems, while providing tools that might eventually allow humans to transform alien worlds into habitable environments for terrestrial life forms. The ethical considerations surrounding terraforming and planetary colonization require careful thought about human responsibilities toward alien ecosystems and potential indigenous life forms. The protocols being developed for planetary protection and ecosystem preservation must balance human expansion needs against the imperative to avoid contaminating or destroying unique alien biologies that might have taken billions of years to evolve. These frameworks are advancing environmental ethics while preparing humanity for the complex moral challenges of interstellar colonization. The economic systems needed to support interstellar civilization represent innovations in resource allocation, trade networks, and economic governance that extend across light years of distance and decades of communication delay. The development of self-sufficient colonial economies, interstellar commerce protocols, and resource-sharing agreements between distant human settlements requires new approaches to economic organization that account for the unique constraints of interstellar distances and travel times. The political structures needed to govern interstellar human civilization must account for communication delays that make centralized governance impractical across cosmic distances. The development of autonomous colonial governments, interstellar confederation systems, and conflict resolution mechanisms that can operate independently while maintaining cultural and economic ties to Earth represents innovation in political science and governance theory, with applications that extend far beyond space colonization. As we contemplate these profound transformations that await human civilization, we must recognize that the journey toward becoming an interstellar species is already changing us in fundamental ways. The technologies we are developing, the international collaborations we are forging, and the long-term perspectives we are adopting are reshaping human society even before our first spacecraft depart for distant stars. The very act of preparing for interstellar exploration is expanding our collective consciousness beyond the boundaries of our single planet toward a cosmic perspective that embraces our role as explorers in a universe filled with wonders we are only beginning to imagine. The decisions being made today about research priorities, international cooperation, and technological development are laying the foundation for humanity's cosmic future. The investments in fusion research, advanced materials science, artificial intelligence, and international collaboration are creating the capabilities that will determine whether our species becomes truly interstellar within the lifetimes of people alive today. The convergence of these various technological streams suggests that the age of interstellar exploration may arrive more quickly than many expect, transforming humanity from a single-world species into citizens of the galaxy itself. The stars that shine into night sky represent destinations that may welcome human visitors within the coming centuries, worlds where our descendants might establish new homes while maintaining connections across the cosmic ocean to the Earth that gave birth to human consciousness. The technologies taking shape in research facilities around the world are transforming these distant points of light from objects of wonder into accessible destinations for human exploration and perhaps permanent settlement. The future that awaits us among the stars may unfold more rapidly than we dare to hope, as exponential advances in key technologies compress development timelines and reduce costs beyond our most optimistic projections. The intersection of fusion energy, artificial intelligence, advanced materials, and precision manufacturing could accelerate interstellar capabilities in ways that transform science fiction dreams into engineering realities within the span of a single human generation. The cosmic ocean that has separated us from other worlds since the dawn of human consciousness may soon become a navigable sea, carrying our species towards shores we can only begin to imagine. And so we reach the end of our gentle journey through the cosmos of possibility, where we've traced humanity's path from a single blue world to the threshold of becoming an interstellar civilization. We've explored the remarkable catalogue of distant worlds waiting beyond our solar system, witnessed the revolutionary technologies taking shape in laboratories around the globe, and contemplated the profound challenges that stand between us and the stars. The answer to our question, can we ever find and travel to another solar system, emerges not as a simple yes or no, but as a story still being written. We have found these other worlds, thousands of them, scattered across the cosmic ocean like islands waiting to be explored. We can envision the technologies that might carry us there: fusion drives that harness stellar fire, light sails pushed by Earth-based lasers, miniaturized spacecraft no larger than butterflies, yet carrying the dreams of an entire species. The timeline stretches across decades and centuries, demanding the kind of long-term thinking that has built cathedrals and founded universities, projects that span generations, yet connect us across time through shared purpose and wonder. The fusion reactors being tested today, the materials being woven atom by atom, the artificial minds being taught to navigate the darkness between stars. All of these are seeds of possibility that may bloom into humanity's cosmic future. As you drift towards sleep tonight, remember that you are living at the most extraordinary moment in human history. You are witnessing the transformation from a single planet species into something far grander. Citizens of a galaxy filled with worlds we are only beginning to discover. The stars above you are no longer unreachable points of light, but destinations calling across the cosmic dark, waiting for the day when visitors from Earth finally answer their ancient invitation. Sweet dreams, fellow traveler in this magnificent journey toward the stars.